Hello, Math 7 students. This is Unit 1, Scale Drawings Assessment Review. Let's get started. Problem number 1. The figures below are scaled copies. Use the information in the diagram to answer the questions that follow. You can see below I'm being asked what is the scale factor to go from the smaller figure to the bigger figure, as well as what different angle measures might be and what different segment lengths might be. To find the scale factor, we first need to find corresponding segments that have information that I can use. For example, we can see this segment here corresponds with this segment, but this one is just labeled as C and this one has an actual measurement. If I keep on looking, I can see this segment is measured as 6 centimeters and its corresponding segment is measured as 18 centimeters. That means I have corresponding segments with information that I can utilize to find the scale factor. Scale factor is the number that we multiply by. So when I'm asking what is the scale factor, I'm asking how do I multiply to go from 6 centimeters to 18 centimeters? For many of you, that might already be a mental math problem. In case it is not, remember, you can always rewrite multiplication to be division. 6 times blank is equal to 18 can be rewritten to be the related division fact 18 divided by 6 is equal to that same mystery number. The reason this is helpful, you can type in 18 divided by 6 into your calculator and it will give you a number. This is a lot harder. You would have to continue to guess and check to figure out what number goes here. 18 divided by 6 is equal to 3, which means our mystery number is also equal to 3. So I am multiplying by 3. 6 times 3 is equal to 18. The scale factor is 3. That means I can use that to find all of the remaining segment lengths. For example, this segment has a length of 3.5, and 3.5 will be multiplied by 3 to give me the segment length for E. 4 will be multiplied by 3 to give me the segment length for F, and so on. So let's go ahead and do that. 3.5 multiplied by 3 is equal to the length for E, and that is going to be 10.5 centimeters. 4 centimeters will also be multiplied by 3, and 4 times 3 is equal to 12, so the length of F is going to be 12 centimeters. So I already, going out of order here, but I know that E is 10.5 centimeters, and F is 12 centimeters. I can also use this information to work backwards. So going forwards, I would multiply by 3, but here on C, I don't know what that number is, but I know that when I multiplied by 3, I got 21. Again, that means if I know how to go forwards, I also know that I can reverse that, and if I'm reversing it, that means I'm going to be dividing. So going forwards, I multiplied by 3, so going backwards, I will divide by 3, and 21 divided by 3 is equal to 7. So length C has a length of 7 centimeters. One of the things that we need to remember about scaled copies is that the angles in a scaled copy do not change. For example, this angle here, even though the side lengths all are multiplied by 3, the angle itself does not change. I'll trace an angle so that you can see that. When I copy that angle, when I pick it up and move it over, let me try that again. When I pick up this angle and move it over, you can see it aligns perfectly. The angle itself does not change. The reason why that's important is because I'm asking for the angle measure for D and the angle measure for B. So since angle measures themselves do not change, if this angle here is 70 degrees, then its corresponding angle in the new figure is going to be the same. It is also going to be 70 degrees. But it also means that this angle up here that has a measure of 50 degrees didn't change from its original, so this angle measure is also going to be 50 degrees. Okay, let's move on to problem number 2. Number 2, a scale drawing of a swimming pool says 2 centimeters represents 7 meters. This means we already have a scale drawing. The scale drawing appears to be measured in centimeters, and it represents an actual distance in meters at the swimming pool. Because it says 2 centimeters represents 7 meters. That is what we call our scale. For all of these types of problems, I encourage you to organize your information in a specific way. So I'm going to do that right now. We had a column where we would write the drawing, all of the measurements we found in the drawing, and a column where we would relate it to all of the measurements in the actual figures. And I always like to start with the scale. So again, our scale says 2 centimeters represents 7 meters. Here's some things to keep in mind. In the drawing, I'm measuring in centimeters. In the actual real world, everything is going to be measured as meters. We also have an important relationship here. 2 changes to a 7. This one is not quite as straightforward as our mental math in the previous problem, but I still want to ask, how does a 2 change to a 7? If you can do it with mental math, that's great. But remember, anytime I don't know how to go forwards with multiplication, so 2 times question mark is 7, we can always work backwards and divide. So working backwards, that would be 7 divided by 2 is equal to that question mark. Type that into your calculator and you will get the fraction 7/2, or that's equal to the decimal 3.5. So 2 times 3.5 is equal to 7. That really helps out. So when I get to part A, where it says the distance on one edge of the pool is drawn as 8 centimeters, how long is the actual edge of the pool? That means it's drawn as 8 centimeters. I have a length that's going to go in the drawing. And I'm asking, how long is it going to be in the actual? Well, that's what I'm going to find out right now. But remember, we know how to go forwards by multiplying by 3.5. So I'm going to take that 8 and multiply it by 3.5. Let's type that into our calculator. 8 times 3.5 is equal to 28. So again, I did that just by multiplying by 3.5. Don't forget, in our drawing, we're measuring in centimeters. In the actual, we're changing our unit of measure to meters. So how long is the actual edge of the pool? It's 28 meters long. Part B says the stairs to the slide are 3.5 meters from the edge of the pool. How far will that be on the scale drawing? So even though I wrote the drawing and actual and scale in the previous problem, this is all still related, so I'm not going to take the time to draw that again. Instead, I'm just going to continue on with these columns through those words. So the stairs to the slide are 3.5 meters from the edge of the pool. The fact that it said meters tells me that we're talking about the actual pool and not just in the scale drawing. So 3.5 meters is our actual distance. And what we're asking is, how far will that be on the scale drawing? So I'm trying to figure out what's going to go over here. Remember, if I'm going forwards, I'm multiplying by 3.5. So if I'm going to be going backwards, that means I'm going to divide by 3.5. Type that into your calculator. 3.5 divided by 3.5 is equal to 1. And remember, our units of measure in the drawing are centimeters, so that will be 1 centimeter. There's some other really great relationships that I would like to draw your attention to, and that is, you can see that 2 multiplied by 4 is 8, so you can also multiply by 4 in the actual. 7 meters times 4 is equal to 28 meters. So that gives you another option that if you're not sure how to go forwards, you can always try converting this way. And that also works here as well. You can see that 7 is divided by 2 to get 3.5. So I could have taken that 2, also divided it by 2 to get 1. Let's move on to question 3. Here is a polygon. Draw a scaled copy of the polygon with scale factor 3. And secondly, draw a scaled copy of the polygon with a scale factor of 1/2. Remember that scale factor is the number that we multiply by. So that means all of the lengths will need to be multiplied by our given scale factor. Let's do A first. I'm going to start the figure right here in this corner. One of the things that I need to do to set me up for success, I need to count or measure every single length that's in this figure. So I'm going to start with that. This is the length of 2. This has a length of 4. When I get to the diagonals, one of the things we need to remember is that we cannot count diagonals just by saying, oh, that goes through 3 boxes, because I could have another diagonal that also goes through 3 boxes, but that's going to look very different. And so whenever we talk about diagonals, I gave the analogy that you live here and your friend lives here. A bird could just fly directly over all of those houses, but we're humans. We cannot fly over the houses. We have to walk on sidewalks and streets. So imagine, again, this is your house and this is your friend. We have to stay on the sidewalks. I have to walk down and over. And that's the distance that we would like to count. So again, to go from here to here, I have to count down 1 and over 3. I always like to draw a dashed line so that I remember that those are the footsteps and not actually part of the actual figure. So down 1 and over 3. And the final piece is going to be from here to here. And again, the bird could just fly directly over the houses, but we are a human and we have to walk over 1 and up 3. So now, when I'm doing a scale factor of 3, all of those distances, all of those lengths, need to be multiplied by 3. So 2 times 3 is 6. This new length is going to be 6. So I'm going to count down 1, 2, 3, 4, 5, 6. This length is a length of 4, and 4 needs to be multiplied by 3. 4 times 3 is 12. So I'm going to now go over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now we get to the diagonals, and remember the diagonal, the red one, I went down 1 and over 3. Well, down 1 needs to be multiplied by 3. Down 1 times 3 now means I'm going to go down 3. And over to the right 3 is multiplied by 3, which is now going to be over to the right 3 times 3, which is 9. So from here, I'm going to go down 3 and over to the right 9. I need to count that again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now that I know how to get to that friend's house, now I can draw the path that that bird would take. And for the last one, the green one, I went over 1 and up 3. But over 1 is multiplied by 3, which means now I'm going to go over 3. And up 3 multiplied by 3 now means I'm going to go up. 3 times 3 is 9. So from here, I go over 3, up 9, 7, 8, and 9. And now I can draw the path that that bird would be able to take. And there is my scaled copy with scale factor 3. Now I'm going to repeat that process, only now my new scale factor is 1/2, so all of my lengths will be multiplied by 1/2. This time it's going to be a much smaller figure, so I will go ahead and start the figure right here. And 2 multiplied by 1/2 is the length of 1. So now I will go down just 1. And 3 multiplied by 1/2. Oops, wrong one. I'm sorry. 4 is the length that I should have done. This length here of 4. 4 multiplied by 1/2 is the length of 2. So I'm going to go over 1 and 2. Now, again, I have my down 1 and over 3. If I'm going to be doing this piece right here, down 1, over 3. But down 1 is multiplied by 1/2, and that is going to be 1/2. I will now go down only half of a box. 3 over 3 is multiplied by 1/2, and over 3 multiplied by 1/2 means I'm now going to be going over 1.5 or 1.5. So from here, I'm going to go down just 1/2 of a box and over 1 and an extra half. I'm going to go ahead and draw that straight line. And now for our final piece, I go over 1 and up 3. Remember, I'm doing this piece right here, over 1, up 3, but everything is multiplied by 1/2, so over 1 times 1/2 is over 1/2. Up 3 is multiplied by 1/2, and 3 times 1/2 is 1.5, so I'm going to go up 1.5 or 1.5. So again, I'm going over 1/2 and up half and an extra 1 to close up that figure. And there is my scaled copy with scale factor of 1/2. Let's move on to the next problem. Number 4, a scale drawing of a construction site is 15 centimeters wide and 25 centimeters long. The actual construction site is 450 meters wide. What is the scale being used is the first question that's being asked. Now, this is similar to our swimming pool problem, but the way that it's different, instead of the scale being given, I'm given measurements from the drawing and measurements from the actual, and I need to use that to figure out what the scale is. So I'm still going to start it in the same way as before, where I list the drawing and I list the actual. I'm still going to have my 2 columns. And I can see that the scale drawing is 15 centimeters wide. That's the drawing, so that's 15 centimeters. The one thing I'm going to do different this time that I didn't do before is I want to make sure that I label this as the width. So I'm going to say this is how wide it is. And the next piece says it is 25 centimeters long. So this is going to be the length. Both of those are measured in centimeters. They're both on the scale drawing. The actual construction site is 450 meters wide. So this is why I use those labels. That 450, when I'm trying to figure out, well, what does it match with? Does it match with this or this? It says it's wide, so I'm going to match it with the one that said wide. So that 450 is going to be listed here, and it's 450 meters. So again, let's pay attention to 2 things here. Centimeters in the drawing are going to be changing and representing meters in the actual, but we also want to see what's the relationship between the numbers. How does a 15 change to a 450? That's something that we're going to answer in the future problems, but for right now, where it just says what scale is being used, this is the scale. A scale simply asks, what is the relationship between the drawing and the actual? That is the relationship. So I can simply say 15 centimeters represents 450 meters. That is the scale. Now, sometimes we do like for this information to be simplified. So if you can find a common factor, then you can divide it out. For example, 15 and 450 have a common factor of 15. So I could use my calculator and divide by 15 and divide this by 15. When I do that, all I'm doing is simplifying the scale, and it's completely optional. 15 divided by 15 is just 1 single centimeter, and 450 divided by 15 is equal to 30 meters. So I could simplify the scale if I want to, and now say 1 centimeter represents 30 meters. Part B says, how long is the actual construction site? So again, this is where those labels are really helpful. The length in the drawing is 25 centimeters, and I need to figure out how long that actually is. In order to do that, I need to, again, find that relationship. How does this 15 change to a 450? The good news is, if we've already simplified here, it becomes even easier. How does a 1 change to a 30? Well, we just multiply by 30. That's the same thing that's happening here. But again, let's pretend like we didn't simplify it. If at any point we do not know how to go forwards, I always say work backwards and divide. So I could have typed into my calculator 450 divided by 15 is equal to 30. And that tells me that we are multiplying by 30 as I go forwards. So what am I going to do with this 25? I'm just going to multiply it by 30. Let's get our calculator to do that. And I'm typing in 25 times 30 is equal to 750. Again, remember, we're measuring in centimeters in the drawing, so in the actual, I'm changing that unit of measure to meters. How long is the actual construction site? 750 meters. Part C. If they wanted to put a fence around the entire construction site, How much fence would they need? I think drawing a picture is going to be a great way to visualize this. So all I know is that we have a height and a width, so I'm going to draw a rectangle, I guess a length and a width. And I know, since we're building our fence around the actual construction site, we're not going to put a fence around the drawing. We're going to put it around the actual. When I label this, I'm going to label it with the actual measurements. So this will have a length of 450 meters, and this will have a length of 750 meters. Fence is perimeter. If I'm building a fence, I obviously want it to go around the outside. So this is a perimeter question, and when I draw the picture, that makes it even more clear. If I want fence, I'm going to need 450 meters of fence here and another 450 meters of fence here. But I'm also going to need 750 meters of fence here, which means I'm also going to need 750 meters of fence there. So I simply need to add up all of those lengths. 750 plus 750 plus 450 plus 450. Again, use your calculator here. And we get 750 plus 750 plus 450 plus 450 is equal to 2,400 meters. The next question is, what is the actual area of the construction site that would be blocked off by the fence? So I'm asking, what's the area? If there is fence going around here, all of this area is inaccessible. So how much area is that? Again, area, remember, is simply length times width, or base times height. So all I need to do is take my 450 and multiply it by 750. And I get, ooh, that's a big number, 337,500. Now remember, our units change here because I multiplied meters with meters, so I get meters squared. Let's move on to the next problem, problem number 5. The pair of figures below are scaled copies. Now again, remember, if it tells me that they're scaled copies, all I have to do is remember the characteristics. I don't have to find information to see if they are. I just need to know that they are scaled copies and remember certain characteristics. We need to circle all of the true statements. So I'm going to read each statement and decide if it's a true statement or not. Segment FG corresponds to segment ST. So let's highlight those. Here is FG. Does it correspond to segment ST? S to T. It looks like those figures, those line segments that I just drew, are in completely different places in that figure. So no, they are not corresponding segments. B, the scale factor from the smaller figure to the bigger figure is 2. I'm going to find something that's easy to count and measure. For example, I'm going to count from F to L. That has a height of 4. The corresponding segment is Q to W, and that has a height of 6. If the scale factor is 2, then that means 4 times 2 is 6. But I know that 4 times 2 is not 6. So this cannot be true. The scale factor is not 2. I don't know what it is. I don't even need to find out what it is. I just know that it's not 2. Point J corresponds to point U. So here's J, here's U. Those look like they are in the same place, the same position, just in different figures. So yes, those are corresponding points. And the last one, angle LKJ, L to K to J, has the same measure as angle WVU, W to V to U. And it looks like in both of those, I traced out the same angle. And remember, corresponding angles are congruent. They're the same. They don't change the angle measure. Segments would change, side lengths would change, distances would change, but angles do not. So if I were to pick this up and move it over, I can see that, yeah, indeed, that matches up. Those are the same angle, so I will be marking that as true. They have the same measure. Okay, let's finish up. It looks like I misnumbered, so I have another problem number 5. And in this one, it says triangle S and triangle L are scaled copies of one another. So again, we already know they're scaled copies. Part A is, what's the scale factor from S to L? So since I know they're scaled copies, I'm going to focus on just one single measurement in each figure. I can decide for the height. I can count the diagonals. The only thing that is the easy thing to count is going to be the bases. So S has a base of 2 and L has a base of 4. Remember, scale factor is what we multiply by. So what number am I going to multiply by to turn a 2 into a 4? Again, hopefully that's mental math for you. If not, work backwards and divide. But 2 times 2 is equal to 4, so the scale factor from S to L is 2 because I multiplied by 2. What is the scale factor from L to S? This is where it gets to be interesting. If I'm reversing this now and I'm going from L to S, I'm saying, how does a 4 multiply and become smaller to be a 2? This is where I want to be careful, because although we recognize that going forward I might be multiplying, then that means going backwards, yeah, I would divide. However, scale factor is a number that we multiply by. So dividing by 2 doesn't answer the question what we multiply by. That's why rewriting it like this is going to be really helpful. And again, remember, if you don't know what this is, rewrite it as a related division problem. We can write this as 2 divided by 4 is equal to that same blank. And now we can type that into our calculator. 2 divided by 4 is equal to 1/2 or the decimal 0.5. The reason I prefer the fraction 1/2 is because I know what problem C is going to ask, and this is a really great trick if you know it. Remember that 2 can be written as 2 wholes as a fraction, or 2 over 1. And the reason that's important is because of this. If going forwards I multiply by 2, going backwards I multiply by 1/2, here's that relationship. When I write the 2 as 2 over 1, all I need to do is then flip that fraction upside down. We call that the reciprocal, and I get 1/2, which is the number I'm multiplying by as I reverse it. So going forwards, I multiply by 2, also known as 2 over 1. Going backwards, I multiply by the reciprocal, 1 over 2, or 1/2. And that's especially helpful when I get to problem number C, where it says, well, imagine there is another triangle that's M, and M is also a scaled copy of S. And in order to make M, they multiplied to go from S to M. The scale factor was 5/2, so I know that I was multiplying by 5/2. What would it be if I reverse that and I want to go back from M to S? What is that scale factor going to be? Well, using that same trick from our last problem, understanding reciprocals, 5/2 flipped upside down to its reciprocal would be the fraction 2/5. So if I'm going from M to S, I would be multiplying by the reciprocal of 5/2, 2/5. And here's our final problem. Below is a polygon on a grid. Draw a scaled copy with scale factor 3. Label the new shape B. So I'm going to, just like I did before when I was doing a scale factor, I'm going to count and measure everything. So this has a length of 3. And with the scale factor of 3, that means that's going to be multiplied by 3. So 3 times 3 is 9. That new side in the new figure is going to have a length of 9. So I'm going to draw it here. 1, 2, 3, 4, 5, 6, 7, 8, 9. This has a length of 1. 1 multiplied by 3 is 3. So that length is now going to have a length of 3. And I'm going to keep on going around and around. This has the length of 2, and 2 multiplied by 3 is 6, so that length is now going to be 6. This is the length of 1. I've already done that. 1 times 3 is 3, so that is now going to have a length of 3. Another piece that has a length of 1, already done that as well. 1 times 3 is 3, so down 1, 2, and 3. And the last piece has a length of 2. Already did that. 2 times 3 is 6. So 1, 2, 3, 4, 5, and 6. Don't forget, it says label the new shape B. So this is going to be figure B. Part B now says, what is the area of figure A and what is the area of figure B? Remember, area is the space on the inside. So in our last problem, I found the space on the inside by doing some multiplication. If I wanted to know what was there, I simply multiplied. Now this is an irregular shape, so you can still find ways to multiply. You would have to decompose and compose, but I put this one on a grid for a reason. So you can simply count the boxes on the inside. 1, 2, 3, 4. That means figure A has an area of 4 because there are 4 squares on the inside. So we can say 4 square units. We'll do the same for figure B. This one's a lot bigger, so let's count it all out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, and 36. So B is equal to 36 square units. Our final question. The scale factor that we use to create figure B is 3. Remember, every length we multiplied by 3. But what is the scale factor in the area to go from figure A to B? We just found the area of 4 square units and 36 square units. Notice, we're not still multiplying by 3. 4 times 3 is 12, not 36. So what is that new scale factor? Again, what I'm really asking is, how does a 4 multiply to become a 36? What am I multiplying by? If you ever can't do it in your head mentally, then work backwards and divide. 36 divided by 4 is equal to 9. That means 4 times 9 is equal to 36. So the scale factor in area is 9. The real question we really want to ask is why? Why is it 9 when all of these lengths were multiplied by 3? How come it's not multiplied by 3? And a great way to demonstrate this is by looking at this piece right here. Now this piece is just one single square. That would represent this piece over here in our new figure. And that same piece now, instead of being composed of just one figure, now has, or one box now has 9 boxes in it. Why? Well, because this piece right here grew 3 times this way, but it also grew 3 times this way, which means that one square grew 9 times total. 3 in our length and 3 in our height. So when the rest of the figure, when all of the lengths are multiplied by 3, this is multiplied by 3, the area itself is multiplied by 3 times 3. In other words, it's multiplied by 9. That's it for this review. Thanks for watching. We'll see you next time.